Thank you. Oh, there are very special feelings on my side, I have to say, because, well, I've been living with Job for more than half of my lifetime as a researcher, and I have this picture. I should have a... Okay. I missed the picture. I had a picture of myself in Geneva for the Year of Polar Prediction Initial Summit. I was in 2015. I started research in 2009, so more than 50% of my time has been with Job. And I have to say it was, well, a very long adventure, very thrilling adventure as well. Probably most of the people in the room I didn't know before the Job Summit, and now I've met a lot of friends, a lot of people. And I would like to thank two people in particular. First is Thomas, of course. Thomas, I don't understand why he's not here. It's really unfortunate, and that's irony of Mother Nature. But anyway, Thomas, I think you've been shown very great leadership for all of what you've done, and I still owe you a glass of wine somehow, and I think I will come and exfiltrate you out of the hotel room somehow and give you that glass of wine. And the other people I would like to thank is Dave Bromwich, who is standing here because of the strong leadership on the southern hemisphere component of the Year of Polar Prediction. And in a way, you managed to tilt the balance and the scale to the southern hemisphere. Otherwise, it would have been a northern hemisphere only component, which would have been a bit of a shame. I would like today to talk about APPLICATE, and I should acknowledge first the long list of authors. I'm François Massonnet, but Irina Sandu was a key player in the work that we undertook in APPLICATE. Irina is now busy trying to solve exciting problems related to high resolution in particular. And what we did in this project is essentially three things. So APPLICATE, if you want to summarize it, is a European project funded by the Horizon 2020 framework program, and it rests on three pillars. The first pillar is the predictions aspect and the predictability, which we know in polar regions is highly challenging. The second aspect is the linkage aspect of those predictions, so trying to understand if better uptake of observations, improved numerical models, improved data assimilation techniques would have impacts well beyond the polar regions, in particular over Europe. And the last mile of the research would be to make sure that the research goes beyond the scientific community and reaches people who need this information most. And we have been in contact with reindeer herders, we have been in contact with the energy sectors, with many policymakers, with schools, so showing that research doesn't stop at the edge of science. Today I'd like to speak about observational data gaps in the Arctic and what we can do about it to try to design the future of observing systems in the Arctic. If you want to understand the problem, well, you can first look at this picture, which takes a bit of time to process, so let's go through it together. You have two panels on the left and on the right. The left is for the winter, the right is for the summer, and then each of the rows of the figure shows a latitude band. So we start at the equator at the top, at the bottom, and then we go up to the North Pole at the top. For each of the latitude bands, you can see multiple lines. The full length of the lines indicates the number of observations that are available on that day to assimilate in the ECMWF forecasting system for a particular year, and that's the year 2019. It doesn't really matter, but that's the number of observations that we have available to assimilate. And then if you notice, for each latitude band and for each season, there are two colors, light blue and dark blue, or light yellow and orange. And these refer to either conventional observations, so those taken on the field, while the light ones are satellite observations observed well, remotely. Also, what you can notice is that the plain bars don't go the full length of the bar, so there is some some gap between what we can actually use and what we can assimilate in the forecast system and what is available. So if you make the ratio between the length between the solid, the plane lines and the hatchet line, then you have how much data was used or wasted, depending on how you see it, from the system. And what is really interesting first is to see that if we go to the northern hemisphere and we go to the polar regions, then conventional observations are actually pretty sparse, and that's not a surprise. They are much sparser than satellite observations because satellites fly over the Arctic many times a month, and so it's really data rich, really data dense in terms of satellite data, but really data poor in terms of conventional observations, no surprise. Then the second observation is that a lot of observations are actually not used. They're just left aside. They're dismissed, or they're misused, or they are just ignored, which is a shame. And a legitimate question would be to ask what happened if we would assimilate more observations into our numerical weather prediction or climate prediction systems. And besides that, we know that the skill of current systems is quite limited in polar regions at subseasonal to interannual timescales. And so the question that we wanted to ask in this project was, well, what would happen if we would take up more observations in our systems in terms of skill? Would we improve the weather predictions, the sea ice predictions, the predictions outside the Arctic first? And then the second question is more controversial. We asked, okay, now that we have this hypothesis that observations could help improve the prediction skill, could we turn the problem around and ask whether the climate models themselves or the numerical weather prediction themselves could be instrumental in driving the development of observing systems? So could we use climate models as a tool to understand what would be the ideal Arctic observing system network in the future? So the goal was really to come up with a set of very concrete recommendations, and I think we succeeded, as I will show in a moment. So 3 examples that I would like to flag here. The first one is about more weather forecast, the second one is more about the sea ice observations, and the third one is about sea ice prediction. Let's go with the first example that's taken from a very nice study that was already mentioned by Thomas, and the study was led by Johnny, who is in the room here. So what they did is that they look at the ECMWF forecast out to 4 days into the future, and a very common practice in sensitivity experiments that people do with numerical weather prediction or climate prediction systems is that they ask the question, what if? What if we denied information? What if we withdrew data from our data simulation systems? What would happen on the scale of the system? What you see on the screen is a difference in root mean square error, so it's a measure of error, telling you what happens if we remove in situ observations from within that pink circle, so that's the Arctic region. What happens if you remove in situ observations from the data simulation system of ECMWF system? What happens in terms of forecast error for the 500 hectopascal geopotential height? What you see is obviously that there are some increase in error within the pink circle. That was to be expected. But the most interesting feature is that in the Siberian side of the subarctic, you have major increases in Z500 hectopascal errors. And actually, we know that these 2 regions, the Arctic and the Siberia, are highly dynamically connected. So it's not a big surprise to see that increase, but it shows that what happens in the Arctic, of course, is not staying here in the Arctic, also valid at weather timescales. And in fact, if we look at when this kind of increases in error happen, then we see that if we have situations of strong anticyclonic blocking over Scandinavia, which favor the advection of air masses into the Siberia, so these are when the the bottom black line here are on the positive phase, then we see that the increasing error is maximal. So it makes a consistent story that there is a lot of potential of using those observations in the Arctic, especially during these phases of the Scandinavian blocking. Second story, sea ice. You probably know that sea ice is a very heterogeneous medium with a lot of variability at the multiple scales. And one question that we wanted to ask is, can we be a bit smarter than going for every meter of sea ice and starting drilling a hole to measure the sea ice thickness? And actually, you would expect that there is a lot of autocorrelation in space in your sea ice field. Of course, if you go here and then you go the next centimeter, the thickness will be the same. It might not be the same if you go 5, 10 meters away, but on large-scale averages, we could expect the sea ice thickness field to have some strong autocorrelation patterns in space. And so we asked the question, what is the minimum number of ideal sampling sites that we would need to reconstruct most of the sea ice volume variability at interannual timescales? So for this, we conducted a statistical analysis with many climate models, and we found, according to several models that we had, that if we choose carefully and smartly 10 stations, ideally placed in the Arctic domain, which you can see on the left screen of on the left panel of the screen, then if we would measure sea ice thickness continuously at this location, then we would have up to 70% of variance explained in terms of global sea ice volume variability. And that's a very strong result because it means that we can constrain the sea ice volume by just picking a few measurements, at least according to climate models. Of course, there are limitations to that. You can ask whether the climate models themselves have the right autocorrelation patterns. That's maybe not the case, but still it indicated that there is a lot of promise there. That's an example where we submitted some policy brief for policymakers, and they were really interested in understanding what was the science behind that, but also seeing the practical implications. And I think that one of the messages of APPLICATE is that if you tell people a story, or if you tell policymakers a story and not just scientific results, then they start to understand what you are doing. Third, but not least, sea ice prediction. And I want here to give credit to Ed Blockley and Drew Peterson. I think Drew is with us here. I think I've seen him. Sea ice prediction has been really booming over the past 15 years. Let's put us back in 2007. The first sea ice minimum happened, and there was really no predictive models for sea ice, or there were a few statistical forecasts, but the dynamical models were really far off. And so it started to spur some interest in trying to predict the sea ice conditions in September, starting from May or from June. And over 15 years, I think a lot of progress has been made, not only in measuring sea ice thickness and measuring sea ice concentration from satellites, but also in the way we assimilate this information into dynamical models. And what you see on the screen is a sensitivity experiment led by the group at the Met Office, where on the left, they in both cases, they wanted to reproduce the 2012 sea ice minimum that occurred in September. And on the left, they didn't assimilate any sea ice thickness information. So they started the simulation on the 1st of May with information they had from sea surface temperatures, from sea ice concentration, if I'm correct. And then they tried to forecast the sea ice minimum in September. And as you can see, the orange sea ice edge has probably the right sea ice area, but for the wrong reasons, because it had a lot of compensation of errors spatially. Then on the right is exactly the same simulation where information from sea ice thickness was assimilated into the model. So the model was able to take into account initial information from sea ice thickness. And we know from early predictability studies, led, for example, by Edward Blanchard, who is with us as well, that there is a strong relationship between sea ice thickness anomalies in late spring, early June, and sea ice area anomalies in September, just because of basic thermodynamic sea ice. When it's thicker, it takes more time to melt, and so it's pretty straightforward. But assimilating that into a system is another job, and they were able to do it, proving consistently that sea ice thickness would improve drastically the scale of those predictions, and also opening a lot of interesting avenues for prediction of shipping routes, for example. So in terms of recommendations, I think we can be really proud in Europe, in the polar prediction projects, in APPLICATE as well, to have come up with very concrete recommendations. And when I mean concrete, is recommendations that can be transferred directly to policymakers, and we know that they would integrate that into future funding offers, or they would put that at the agenda of future polar research. We have written a summary paper about that. I would go quickly through several of those recommendations. The first one would be to make sure that we have some continuity in the sea ice thickness data records. And why do we need that? Well, because currently there are a couple of space missions going on, for example, ISAT-2, Cryosat, but these missions can theoretically come to an end if the instrument fails, and that could be around 2024, 2025. The problem is that the next mission from the EU, as far as I know, is Crystal, and it's due to start in 2026. So potentially we could have a gap of 1 year where we wouldn't have any information for sea ice thickness, and that would be a critical problem for reconstructing the state of the system, to measure the trends, to also bias correct the forecast, and also to monitor the real-time state of the Arctic. Maybe the second point I would like to flag is the use of microwave sounding observations to improve the numerical weather forecast. As it's been shown that for winter and summer, it's really important to take this into account if you want to improve the weather forecast. And we are much better positioned now than we used to be a couple of years ago. So what's the bottom line of all the research? What we have understood is that, yes, the Arctic is data sparse, but we don't need more data. We don't think we need much more data than we have today. We need to make a better use of existing data. We need to consider data that we usually waste or that we don't assimilate because it's there and it can bring significant improvements in our prediction systems. We also need to make sure that what is currently in place will remain in place for long, and that there won't be discontinuities in the observational data sources. And last but not least, it's important to have some sort of operational availability of data. When people have started to forecast sea ice, as I explained in 2007, it didn't really matter if the data was coming 2, 3, 4, 5, 6 months later, because people were doing that essentially for academic exercises, for science. But now if you want to be really able to forecast the sea ice conditions in September, we need to have this data at most a couple of days after it's been acquired by the satellites. Otherwise, it's a waste of time, and then September comes and we have the minimum and we didn't see it coming. So it's really important to, for sea ice thickness at least, to try to reduce the time between the measurements is made and it's available as a product. I think I will leave it there. Oh no, yeah, I have this final metaphor that I think will be very nice to hear to Peter, because he mentioned the shadow in his presentation. That's I think a metaphor that has been with me for several years now. You have a floating cylinder in the middle, and that's the truth, right? That's the system you're trying to understand. And that truth is projected on two perpendicular walls. On the one side, you have observations, either conventional or satellite, and that's one way to project the truth. And then you have numerical weather prediction and climate models, and that's another side. And what you see is that these are totally different objects. One is a square and is blue, and one is a circle and is yellow. It doesn't mean one is wrong, one is right, but they are just two versions of the same truth. for long, there's been a lot of use of observations into climate models to make, call it model evaluation or forecast verification. It's been very popular and very helpful. There's been a lot of also effort to trying to, should I press harder? Yeah, so you need to press harder when there's been a lot of use of both climate models and observations in trying to reconstruct the truth, and that's called data assimilation. So it's when you try to estimate the state of a system subject to minimizing errors in a least square sense, for example, knowing the uncertainties of both sources of information. But what is really emerging is this one. Yes, you can use also climate models and numerical weather prediction models to drive your observing system and give concrete recommendations for the next decades or so. Thank you.
Questions? One here first.
Very nice presentation, François. When I looked, 10 years ago, when I looked after the radiosonde network for the Arctic of Canada, I asked the question, because it's very expensive infrastructure in the high Arctic, what would be better? Could I reduce a small number of stations but increase the temporal frequency of observations in the other existing stations, so 4 a day instead of 2 a day? And so if I reduce the network by 25% but increase the temporal releases by 100%, I know it would be a lot cheaper, but can you answer the question that I could not get an answer 10 years ago?
Yeah, that's an excellent question. I'm afraid I don't have the answer. It should mean that we have to look at the spatial correlation of temperature anomalies or geopotential anomalies in the Arctic, which I think has been done in several studies. Maybe Jenny will react to that. Yeah, go ahead.
Yeah, so we used these at ECMWF. We ran some simulations with and without these additional radiosondes that Thomas mentioned that were released during this SOP1. And the impact, I mean, there was a slight positive impact, but it wasn't a game changer. What we didn't do was this other part where we sort of, remove a station or two and then keep them in. But I mean, potentially it's kind of a nice data set for looking at that in the future.
Hi, François. Thank you very much for the presentation. That's very interesting. I think it is very interesting and useful to be using the prediction systems to look at how we can design the observing system. And it was nice to see how you were able to come up with some very concrete recommendations going forward. There's one, however, that surprised me a bit when you mentioned that you thought that one of the priorities was not to observe more, but just how we use it. And I was wondering, in coming up with that, I mean, did you think about, for example, the ocean and its role in transporting heat and nutrients and other things, and its role in interacting with the sea ice and the atmosphere?
Mm-hmm. Yeah, I mean, it was always really, I mean, this kind of statement always rely on some sort of a hypothesis, and this hypothesis here is really the time scale. So we were interested into whether to sub-seasonal to maybe seasonal timescales, where the ocean maybe plays a little bit less of a role than for interannual predictions. But there have been a couple of studies, for example, I think with Mitch Bushuk, where they did some sort of denial experiments in the GFDL models, where they show that it has an importance for seasonal to interannual predictions. So yeah, these statements are conditional to the timescale that we are looking at, and I do think that ocean variables are still important, starting from the end of the window that we looked at further into the future.
Okay, thanks.
Hi, Gita Lubicic from McMaster University. Thank you for your presentation. I have two quick questions. One is, at least in the Canadian context, many Inuit communities are leading their own community-based monitoring and doing a lot of ice thickness monitoring. Is there any way to bring those into your suite of observations to expand those sample locations?
Yeah, if I'm not wrong, the type of ice that they are probably measuring is more landfast ice, which is not simulated in many models used in the climate models so far. So it would require a bit of either model improvement on the climate model side or some sort of observational operator that could be applied to integrate that information. So the problem I see so far is really a problem of scale, is how do you collocate that single point measurement that could be tainted by representativity errors, because if you would have drilled your measurement a couple of 100 meters away, it could have been different. To what sense is that meaningful for the grid cell that is measuring like 25 by 25 kilometers in a climate model? I'm not saying it's useless, but it would require some sort of thinking about upscaling this information.
That's my next question, is what would it take to get land-fast ice more effectively represented in those models?
So what does it take?
Yeah, what would it take to have land-fast ice better represented? Like, I realize the challenges of scale and variability, but that land-fast ice is so important for communities and even for shipping across the north.
It's being actually implemented now in sea ice models, and I'm sure that Jean-François can say a word if he likes. And so it does make an impact to have such sort of landfast ice modules, and that goes back to the point that I was mentioning in the recommendation, is that this improvement in observing systems have to be done synergistically with the development of climate models. It means you cannot start to observe a new variable unless you have a good reason, and here the good reason would be exactly that new climate models in 5 years from now, they will have this kind of landfast ice module. So the short answer would be just wait for another couple of years.
This is not so much a question, but I think what you're bringing up and what I'm thinking about when I'm hearing some of these other presentations, and I would like everybody here to be thinking about this for the rest of the week, is that when we talk about observational data, we have two different kinds of observational data. Well, we probably have lots of different kinds, but two major classifications is the data that's collected by the satellites and the GTS system, which is the kind of data that I think traditionally models use to assimilate and do verification. And I think that the step forward we need to have is using these other kinds of data, community observations, and this process level kind of observations that we take at the observatories and that we were trying to incorporate into the process with the YOP-SITENIP. So when we talk about observations, think about these two different classifications of observations and how we're going to be able to utilize both of them to forward this mission.
Thank you, François. That concludes this session. Now it is time for the photo. The photo is not going to be here. Change of plan. The photo is actually going to be out by the registration table. So if everyone could make their way out this door to the registration table, we'll try to do this as fast as possible so you don't miss too much time for lunch.